Hello lovelies, in this video we're going to be taking you through our Combined Science Foundation Chemistry Paper 1, the predictive paper that we've written for 2024. Now, in this paper we're going to take you through how to lay out your answers, what sort of things the command words are looking for, so please pay careful attention to everything we say.
Calcium reacts with oxygen to form calcium oxide. Calcium is a metal. Here we're asked to complete this sentence using answers from the box. So we know that calcium is a metal because it is found on what side of the periodic table? So the answer to this is the left-hand side. So if I give you a quick reminder of the general shape of our periodic table, what we have is a little staircase that separates the metals from the non-metals. So all of our metals are found over here in this really quite large region on the left-hand side of the periodic table, whereas all of our non-metals are found in this much smaller little portion of the periodic table over on the right-hand side. So the answer to this question is that metals are found on the right-hand side of the periodic table. So the electronic structure of calcium is 2882. Now we're asked to identify which group of the periodic table calcium is found, and we're asked just to tick one box. Well, here of course we could look up calcium in the periodic table if we needed to. We could find our periodic table, look up calcium, and the groups are going to be the column that it is found in. So here though, even without the periodic table, we have enough information to determine what group calcium is in. The number of electrons in the outer shell of an atom is going to be the same as that group number. So here, because there are 2 electrons in the outer shell, we can see that it is going to be in group 2. So that is a great shortcut way to be able to determine the group if we know the electronic structure. But at the same time, you could just have looked at your periodic table and identified where calcium is, and you will find that it is actually in group 2. Looks somewhere like this on our periodic table. So here we're asked to complete the diagram to show the electronic structure of oxygen. So the first thing that I would do in this case is I would go to my periodic table and look for oxygen. So when I find oxygen, I can see that it looks like this on the periodic table. Now this bottom number represents the proton number or the atomic number. And it's important that we know that when we have an atom like we do here, the proton number is exactly the same as the number of electrons. So here we can see that there are 8 electrons in an atom of oxygen. So now we can use this fact to draw this electronic structure. So 8 electrons in total. It's important that we know that in the first shell, so the most innermost shell of oxygen, we can only fit 2 electrons. In subsequent shells, we can fit in as many as 8. But here we just need 8 in total. So we've already used 2, so then we've got 3, 4, 5, 6, 7, 8 electrons. So there, what we have here in this drawing is the electronic structure of oxygen. See, we have 2 electrons in its innermost shell and then 6 in its next shell to represent the 8 electrons in total in an oxygen atom. So now we're told that the reaction between calcium and oxygen is given by 2Ca plus O2 makes 2CaO. So what that's saying is that calcium reacts with oxygen to form calcium oxide. Now we're asked to complete these sentences using the words in the box. So here we're asked, what does calcium do with respect to electrons? Does it gain an electron? Does it lose 2 electrons? Or does it gain 2 electrons? Well, if you remember from the previous part of this question, we were told the electronic configuration of calcium is 2882, where this last 2 is the outer shell of the calcium. To get a full outer shell, that calcium could technically do one of 2 things. It could lose those 2 electrons, or it could gain 6. Now, gaining 6 electrons will be far harder work than just losing 2. So what is going to happen is it's going to take the easiest route, and that calcium atom is going to lose 2 electrons. So we can fill in the blank here. Calcium loses 2 electrons. And then we're asked, what does oxygen do? So we can look at our diagram here. So we can see we've got 2 electrons in the innermost shell and then 6 in the next. And this is a different way of writing the electronic configuration of oxygen. Here we can see that we have 6 electrons in its outer shell. So again, to get a full outer shell, oxygen has 2 options. Either it can gain 2 to get up to that full number of electrons of 8 that it can hold in its shell, or it could lose 6. Now it's going to be much easier to simply gain 2 electrons, and that therefore is going to be what happens here. So we are going to, in this case, gain 2 electrons. And that will ensure that we have a full outer shell in both the calcium and the oxygen. Now we're asked to identify the relative charge of a calcium ion. So there's a few different ways we could look at this. Of course, we knew that its electronic configuration was 2882. And we know from earlier that in order to get this full outer shell that every metal and non-metal is striving for all the time, we are going to have to lose 2 electrons. Now, if we think about this, if we're losing something negative, and don't forget, an electron is a negative particle. It has a charge of -1. If we lose something negative, then we become more positive, even if it's just a negative thought or something. You lose something negative, and in turn you become more positive. So here in this case, when we lose 2 electrons, we're going to become more positive. And so what we have is a 2 positive charge for that calcium ion. As I mentioned, there are other ways of learning this. Without much understanding, perhaps, you could just learn that group 1 always will form an ion with just simply a +1 charge. All of the substances in group 2 will always form a +2 charge, and all of the substances in group 3 will always form a +3 charge. So that could be a simple, quick hack, a quick cheat code for remembering this, but I really, really recommend that you understand where these charges are coming from. And it's simply a case of, are we gaining a negative thing? If we are, we're a negative ion. And if we're losing a negative thing, we're becoming a bit more positive, so we become a positive ion. So now we're asked what kind of bonding is found in calcium oxide. And there's a really quick way to identify what kind of bonding a substance has. What you need to do is to look at what atoms make it up and ask yourselves, are those metals or non-metals? Now, from what we said earlier with the periodic table, calcium is found on the left-hand side of the periodic table. And so calcium is a metal. Oxygen, on the other hand, is on the right-hand side of the periodic table. And so for that reason, that is a non-metal. Whenever you have a metal and a non-metal bonding together, they form an ionic bond. If we just had non-metal atoms together, then they form covalent bonds together when they bond together. And metallic would be we simply have a metal on its own. So in this case, the type of bonding found in calcium oxide is simply ionic. So finally we're asked to complete the dot and cross diagram of calcium oxide. Show outer electrons only. So to do this, we need to remember that electronic configuration of calcium and of oxygen. And the oxygen one, in fairness, we've already drawn the full electronic configuration of it. Here though, you can see we only want to show the outer electrons. If we start with oxygen, just because we drew that earlier, you'll remember that it had 6 electrons in its outermost shell. So we can start by drawing 6 electrons in the outer shell of oxygen. Calcium on the other side, you can see that in its outer shell it only has 2 electrons. So initially it would have 2 electrons in its outer shell. But when this bonding takes place, calcium's 2 electrons are going to get donated to the oxygen. Remember, we said that it is giving up its 2 electrons and becoming 2+, becoming more positive, and the oxygen in turn is going to gain 2 electrons and become 2- in charge. So here, if we remove now these little arrows because we don't need them, you are going to be able to see the dot and cross diagram for calcium oxide. You see that the calcium gave up its 2 electrons, becoming a 2+ ion, and it gave them to the oxygen, which received them to get a full outer shell of its own and become a 2- ion. The reaction of sodium carbonate with ethanoic acid is an example of an endothermic reaction. A method used to investigate the temperature change when 10 grams of sodium carbonate is added to 50 centimetres cubed of ethanoic acid is 1. Place a polystyrene cup inside a glass beaker. 2. Measure 50 centimetres cubed of ethanoic acid and place in the cup. 3. Measure 10 grams of sodium carbonate. 4. Put a thermometer in the cup. 5. Record the temperature of the ethanoic acid. 6. Add the sodium carbonate to the cup. 7. Stir. And 8. Record the highest and lowest temperature reached by the solution. So here in our first part of this question, we're asked to give 2 ways that the method could be changed to improve the accuracy of the results. So in a question like this, we need to look at our method and think, what are we lacking here? So let's look at a few of the things we could do to improve this. One thing is, maybe we can put a lid on our cup. Because the problem is here is when we use that thermometer, some of the heat might be leaking to the surroundings. For 2, we can simply do this whole thing again and repeat it and take a mean. So that's going to eliminate any little anomalies that might pop up, things that we do wrong. Alternatively, some other things you could have said instead. Maybe you could use a more accurate thermometer, perhaps a digital thermometer if we've used an analog one. Or alternatively, on a very similar theme to that, we could use a more accurate balance. Of course, you can see that we're measuring 10 grams of sodium carbonate. What about if instead we had 10.0 or 10.00? Now that would be an example of a more accurate measurement where we've got it to more decimal places. So using a more accurate balance would also be a great way that we can improve the accuracy of our results. So next up, we're asked to suggest why a polystyrene cup was used. So we need to think, why did they choose that material over something else? Why did they not just use a glass beaker or something similar to that? So the reason why we do use this polystyrene cup is because polystyrene is a heat insulating material. So by using this and by doing our reaction in a polystyrene cup rather than an alternative material, we're going to reduce heat loss to the surroundings and therefore make it more likely that that temperature change that we are measuring isn't going to be inaccurate. So now we're asked to explain what is meant by an endothermic reaction. So an endothermic reaction is a reaction which is going to take in energy from the surroundings. So we need to remember that important fact that the energy is taken in from the surroundings. So as this is such an important thing to remember, let me tell you an easy-ish way to remember this little fact. So endothermic, let's think about the word for a moment. So the endo bit is a bit like the word in or into. And thermic refers to heat. So that means that the word endothermic is talking about taking heat in. So then if we look at the word exothermic now, and again we sort of pull that word away and think about what it means. We've got the part of exo, and exo sounds a lot like the word exit, which is like the way out, isn't it? And thermic again is still going to refer to heat energy, just like a thermometer or thermals or something like that. So exothermic refers to giving heat out. And that there is the difference between endothermic and exothermic. So here we're asked to complete the enthalpy profile diagram for an endothermic reaction like that observed between sodium carbonate and ethanoic acid. And we're asked to label the activation energy. So here in this case, we need to know that we start with our reactants. And because it's endothermic, so it's taking energy in, that means that our products are going to end up with more energy than our reactants had. So that means that our products are going to be a horizontal line higher up than the line of the reactants. So then we draw ourselves a nice little hump, starting at the line for the reactants, going above the products, and then ending at the line of the products. So here we're asked to label the activation energy, and the activation energy will be the line starting at the reactants, going all the way up to that peak of our hump that we've drawn on. So this green line, this green arrow represents the activation energy. And here we've correctly labelled on the reactants, the products being at a higher point than the reactants, and included the activation energy. And that is going to be how we get our 2 marks in this question. So here we're asked to identify which of the following is another example of an endothermic reaction. And this is something that we're just expected to know through learning about different examples of endothermic and exothermic reactions. So here the correct answer is going to be thermal decomposition. Now this here is going to be a very standard example of an endothermic reaction. The other 3 examples are all generally going to be exothermic. Combustion, of course, is a reaction where you burn a substance, and we can very physically, noticeably realise that there's a heat given off in that example. Probably one of our more everyday examples of an exothermic reaction that we experience. Neutralisation reactions are also, generally speaking, exothermic. Self-heating cans, well, it's kind of in the name, isn't it? With the switch of a button, the cans can heat themselves up. Now, they can only heat themselves up because they are an example of an exothermic reaction. And therefore heat will be coming out from the chemicals within that can to radiate and heat up that can. When water, H2O, is added to group 1 elements, a chemical reaction takes place. Here we're asked to calculate the relative formula mass of H2O. So in order to do this, you need to go to your periodic table and find the relative atomic mass of both the hydrogen and the oxygen. Now hydrogen, if you identify it in the periodic table, is in a little box with a 1 above and below it. Now there's a little key on the periodic table too, which can help us if we ever forget which number means which. But the top number you will see on that periodic table represents the relative atomic mass. So that means that we know that the relative atomic mass of hydrogen is going to be equal to 1. Oxygen, on the other hand, if we look in the periodic table, has a relative atomic mass of 16. So that means when working out the relative formula mass of H2O, we're going to use the mass of hydrogen being 1 and the mass of oxygen being equal to 16. And when working out the MR of H2O, we need to take into account the fact that we actually have 2 of the hydrogen, so we have 2 of these 1s, and then we've also got an oxygen. So we're going to do 2 times 1 plus 16, which will simplify to 2 plus 16, which is equal just to 18. So 18 is our answer to this question. So now we're asked to describe 2 observations that would be made if a small mass of a group 1 metal was added to 25 centimetres cubed of water. So here this is testing us on our knowledge of group 1 metals and their reactivity. So to be able to answer this, let us first have a remember of what happens when a group 1 metal does react with water. So if we think about this reaction and we work out what the products are, we can see that we have a group 1 metal plus water is going to form a metal hydroxide and hydrogen gas. Now this formula is really helpful when it comes to determining these observations. Of course, ideally, you would have learnt what these observations are and just be able to write them down. But if you don't have these memorised, this reaction here can help you get these observations. Because if we look at this reaction, you can see that we start with having a group 1 metal, but then we end with a solution and a gas. That means that what we're going to observe is our metal will disappear, or get smaller, or even melt. But it's going to visibly get smaller. Another observation that we can use from our reaction that we've got written down here is this formation of hydrogen gas. Now you didn't have any gas to begin with, but now a gas has formed. And as a result, we're going to get some bubbles, or we could say fizzing or effervescence forming. And that would be another observation when these 2 things react together. Alternatively, we might observe a flame, dependent on the reactivity of that group 1 metal. That one's a little bit more dependent on what metal it is, but this question hasn't specified, so we'd still get our marks. And if a flame did form, and of course we've got hydrogen gas being given off, we may even observe a squeaky pop sound. And that would be because, of course, the chemical test for hydrogen, you may not remember this yet, depends on where you are in the course. Obviously, by the time of the exam, you will know this. But the positive test for hydrogen gas is when a flame is present, you will hear a squeaky pop. But don't worry if you're not familiar with that yet at where you are in your studies. Depends on your exam board if that is relevant for this particular paper. But those there are 4 options that will get you a mark if you were to complete this. I would probably go with the metal gets smaller in the bubbles because that's generically always going to be true. But dependent on the metal, certainly we might see a flame and we may even hear this squeaky pop sound. So finally, we're asked to complete the word equation for the reaction of specifically sodium with water. So we've already just used this fact, haven't we? So now we can fill in this information. So sodium plus water will give us sodium hydroxide, that's the metal hydroxide we talked about just then, plus hydrogen. So that there is your general word equation for a group 1 metal, for instance sodium plus water. We're going to get a metal hydroxide, in this case sodium hydroxide, and hydrogen. Noble gases are monatomic and they are unreactive. Give the group that noble gases are found in. So here we should understand that if we were looking at an image of the periodic table right now, the noble gases are found right to the far right-hand side of the periodic table, and they are found in group 0, although sometimes you might see that referred to as group 8. And we're asked here to explain why noble gases are unreactive, and this really does again come down to its location in the periodic table. So looking at the electronic configuration of all of the elements that are in group 0 of the periodic table, all of these noble gases, you will see that they all have 8 electrons in their outermost shell. And for something to react, it wants to gain a full outer shell. It wants to have these 8 electrons in its outer shell. And if it's already got them, well, it doesn't need to react, does it? Because it doesn't need to gain any electrons. It doesn't need to lose them. It just already has that full outer shell. So that reaction does not need to react with anything. And that is why it's unreactive. So if we were to write down that answer, we would explain that it's because it has a full outer shell of electrons. So here you can see that we're given a graph of a few different group 0 elements, so helium, neon, argon, krypton and xenon, and we're given each of their boiling points. And here in this first part of this question, we're asked to describe the relationship between the boiling point of the noble gases and the number of shells that they have. So in order to answer this, we'll probably need to use our periodic tables as well. So we can see that helium simply has 1 shell, neon has 2 shells, argon has 3 shells, and so on. So we can see that the number of shells increases as you go along this axis. Now a little bit of a tip for you in case you weren't aware of it, the period that an element is in is equal to the number of shells it has. So you may well find that little fact very helpful in questions like this. So let's have a think about this then. Let's describe the relationship between the boiling point of the noble gases and the number of shells. Well, here now we can see that as the number of shells increase, so does the boiling point. So we can say that as the number of shells increases, the boiling point will also increase. And that there is all we need to say here to get our 1 mark for this question. So now we're asked to explain this relationship. So we're asked to explain why it is that as the number of shells increases, so does the boiling point. And here we can fortunately see that they've given us some words to use here. So getting started here, we can start by saying that the greater the number of shells a particle has, the greater the size of the particles. Basically, more shells give us a much bigger particle. So the next thing to say after that, and this will be our first mark, what we've just said, but our second mark we will gain by saying that the bigger the particles, the stronger the size of the intermolecular forces between them. So that's a really important link, that as the particles get bigger, the intermolecular forces are actually getting stronger, making them more attracted to each other. And as a result, because they're more attracted to each other, we're going to need more energy to overcome that attraction between them and to pull them apart, and therefore to change their state. So that there will be the final marking point here. So we need more heat energy to overcome these intermolecular forces and to change their state. So now we're told that group 7, such as fluorine, chlorine and bromine, are diatomic molecules. And we're asked to state what the group 7 elements are also known as. And this here is really just a recall question, just a little fact that we're expected to know. So if you don't know that, do stick it on a flashcard and get revising it. So the group 7 elements are otherwise known as the halogens. So that is a fact that we need to know. Now we're asked to complete the sentence about the group 7 elements, and we're asked to put a circle around the correct answer. So moving down group 7, the reactivity, we're asked, does it increase, does it decrease, or does it stay the same? And as we move down group 7, the reactivity is going to decrease. Now we're told that when chlorine reacts with potassium iodide, a reaction takes place and chlorine displaces iodine. Here we're asked to complete the balanced symbol equation for this reaction. So, as we're told, the chlorine is going to replace the iodine in the potassium iodide. And that will result in us forming 2 KCl, because we have just literally replaced that iodide ion with a chloride ion, and I2. And that there will be the balanced symbol equation for this reaction. So now we're asked to explain why chlorine displaces the iodine from the potassium iodide. So to do this, let's remind ourselves of the order of the elements in group 7. So right at the top of group 7, we have fluorine, then we have chlorine, then we have bromine, then we have iodine, and finally we have astatine. So if we refer to our earlier part of this question, we said that as we move down group 7, the reactivity decreases. So we can say at the bottom here that we have the lowest reactivity, and at the top we can say that we have the highest reactivity. So in order to understand why this pattern happens though, let's think of how many shells each of these things have. So fluorine only has 2 shells. Chlorine will have 3 shells. Bromine will have 4 shells. And quite quickly, it's going to get quite hard to draw this, but there'll be 5 shells for iodine and 6 for astatine. So we can see then that there's more and more and more shells as we go down this group. Now let's remember that if we have a group 7 element, the way in which we are going to get a full outer shell will be by gaining 1 electron, because by being group 7, they currently have 7 electrons in their outer shell. Now we need to think, how are we going to gain this electron? We're going to need to attract it, aren't we? Well, in the middle of each of our atoms, we have a positively charged nucleus. So when an electron is coming along, it is going to get attracted to that positively charged nucleus. Now for chlorine, that nucleus is quite close to that outer shell. Whereas with iodine, it's quite far away. It's further away because there are more shells for iodine than chlorine. So the reason why chlorine displaces iodine is due to the fact that chlorine has fewer shells than iodine. And because therefore you've got these fewer shells, we know that there is this smaller distance, and therefore chlorine is going to have a greater attraction between its outer shell electrons and the nucleus. And due to this fact, we know that chlorine is going to be able to gain that extra electron much more easily than iodine will. So that would be how we get the 3 marks in a question like this. We show that we understand that chlorine has fewer shells than iodine. We understand that that means that chlorine is going to have a greater attraction between the outer shell electrons and the nucleus. And finally express that it's going to be able to gain an electron more easily than iodine. And there you go, that is the answer to that question. And if you're not familiar with that, and if that's something that seemed a bit new to you, then this is a perfect model answer to use a flashcard for. So you can always write this question and write this explanation on your flashcard and get learning it. Bauxite is aluminium ore. To extract aluminium, the bauxite needs to be purified to aluminium oxide, and that process is shown here below. Here we're told that the process of electrolysis is used to extract aluminium, and we're asked to describe the process of electrolysis by completing the sentences below. So let's fill these in then. In the process of electrolysis, positively charged ions move to the something electrode. So this is going to be the negative electrode, because positive and negative charges attract. The electrode is called the cathode. So if you're not familiar with that, then do add that to your flashcards, that the cathode is the negative electrode. So while negatively charged ions move to the positive electrode, because again opposite charges attract, which is called the anode. So the anode is the name of our positive electrode. So those are a couple of facts that if you're not familiar with, I would definitely recommend that you make a note of them and add them to your flashcards and get memorising them, because it is a great easy fact to know. So now we're asked to explain why reduction with carbon cannot be used to extract aluminium. Because of course reduction with carbon is an alternative method that we can use for the extraction of metals from their ores, as opposed to electrolysis. But we need to know what is the actual reason why electrolysis would be chosen over the reduction with carbon. And it's all about the reactivity compared to carbon. So the knowledge that we need to use here to explain this is that we can use the method of reduction with carbon to extract the metals from their ores for metals which are less reactive than carbon. So on the other hand, electrolysis is the method we would use to extract metals from their ores if we're trying to extract metals that are more reactive than carbon. So in this case here, the reason why we're asked to explain why reduction with carbon can't be used to extract aluminium, that is simply going to be because aluminium is more reactive than carbon. And that would be our explanation as to why we don't reduce it with carbon instead. So now we're asked to name the material that the electrodes are made of for the electrolysis of aluminium. Now this is just a recall question. We know that because it just says name the material. So we just need to have this fact memorised and be able to write it down. So the answer to this will be graphite. Graphite is a material just made up of carbon, but it is a form of carbon which can conduct electricity. And that is what's very important here. So we use graphite electrodes because they do conduct electricity. So next up we're told that molten cryolite is added to the aluminium oxide to make the electrolyte. And here we're asked to explain why cryolite is added to the aluminium oxide. The equation for the extraction of aluminium from aluminium oxide, Al2O3, is shown below. And we're asked to balance this equation. So here you can see we're told 2Al2O3 makes 4 aluminium, so the aluminiums are already balanced, but we need to say how many oxygens we need to balance this. So looking at this 2Al O3, I can see that I have 3 oxygens, but I have 2 sets of that. So in total, I can see that I have 6 oxygens. So in this formula, I can see that those oxygens are written in the form of O2. So we need to think how many O2s do we need to get 6 oxygens? And the answer will be we need 3 O2s, and therefore we would get these 6 oxygens. So the answer would be 3 to get 6 oxygens. So during this reaction, the aluminium oxide has been, we need to ask ourselves, has it been oxidized? Has it been reduced? Has it been displaced? Or has it been combusted? So here I can see that that aluminium has lost its oxygen, and we know that reduction is the loss of oxygen. So as a result of that, we can tick the box which says reduced. So in this question, we're told that diamond and graphite are allotropes of carbon. And what an allotrope is something which is made of the same atom, but it's just arranged in a different structure to form something slightly different. So here we've got diamond and graphite, both made up exclusively of carbon. So we're given a table with their properties. We're told that diamond doesn't conduct electricity. It has a very high melting point of 4,000 degrees C, and it is very hard. Whereas graphite is a good conductor of electricity. It's got a lower melting point of 3,600, and it is soft. So some very different properties there. Now these 6 markers are a little bit different to a normal question. Because with a normal question, you would think, oh, it's a 2 marker or a 3 marker. You need to give that many marking points. You need to say that many significant things to get those marks. And here, although this is a 6 marker, certainly giving 6 points would be good. That isn't necessarily what's going to get you the marks. Because if you gave 6 marks about diamond, you probably wouldn't actually get many marks. Because what these 6 markers are looking for is they want you to give a high level of detail and talk about all relevant points. You want to give a full answer discussing a bit of everything, nicely balanced. But you're not necessarily going to get it for just six facts that you lay out that's relevant. It has to answer the question fully to a high level of detail. So let's have a look at how I would suggest answering this question. So here I'm going to start talking about diamond, and I'm going to discuss the structure and properties that diamond has that makes it distinctive and special, and then we'll link it to its properties. So in diamond, every one of its carbon atoms forms 4 strong covalent bonds to other carbon atoms. Now that is very, very distinctive of the carbon atoms in diamond. So now we've talked about the bonding, let's mention the type of structure that diamond has. So diamond has a giant covalent structure. So let's link all this now to the properties. So we've said, haven't we, that diamond has a very high melting point of 4,000 degrees C, and it is also very hard. So we need to describe why it has those properties and how it links to what we've said about the bonding and structure. So the reason why it has that very high melting point and it's very hard is because of those strong covalent bonds. It is going to take a lot of energy to overcome those bonds and to break those bonds. That is going to have a direct impact on this high melting point and it being very hard. So the next thing that we want to talk about here is why is it that it doesn't conduct electricity? Well, if we look at each carbon atom would normally have 4 electrons that it could donate to form bonds, and every single one of those does form bonds because it has 4 strong covalent bonds. As a result, there's no spare electrons, there's no delocalized electrons that would be what's needed to conduct electricity. So that's why diamond doesn't conduct. Let's get on to graphite. So in graphite, each carbon atom only forms 3 of these strong covalent bonds. So it doesn't form the 4 that diamond did. And that's one of the main differences between diamond and graphite. So if you're not 100% familiar with those differences, then I would definitely recommend that you make yourself a little flashcard with a nice table comparing the 2. So graphite, we've mentioned that each carbon forms only 3 strong covalent bonds. Now we can link it to the properties of graphite. So we can see in the table that there's a lower melting point for graphite and it's also soft. And the reason for that is that graphite forms layers. And those layers, they don't have these strong covalent bonds between them. They've only got weak intermolecular forces. And as a result of these weak intermolecular forces, it's going to be really quite easy to overcome these forces. And so for that reason, we don't have as many strong bonds to break. We've got some that are actually quite weak. And then we have that knock-on effect there of that lowering the melting point and making it softer. So then the final thing really to mention about the properties of graphite is going to be about the fact that it is a good conductor of electricity. So if we think back to the fact it only forms 3 strong covalent bonds, and carbon, of course, it has 4 electrons in its outer shell. So if only 3 of those has gone to form covalent bonds, then we're going to have 1 left. And that one that's left is delocalized, which means that it is going to be free to move through the layers that are formed in graphite, and it can carry that charge. And that there is what's required for something to conduct electricity. So that is why graphite is a conductor of electricity, because it has delocalized electron which is free to move through the layers. So let's just look at some of the key facts that's important to know about diamond and graphite, the key words that are going to bring you in the marks in an exam. So for diamond, knowing that you have 4 strong covalent bonds, that you have a giant structure, and then for graphite, that we only have 3 strong covalent bonds, and that we have layers formed. Also, the fact that graphite has 1 delocalized electron for every carbon, and in diamond you actually have no delocalized electrons. If we were to strip back everything here that we have said, those are the key facts that you can link to anything if you learn those. So I'd really recommend that you learn those key facts, draw up a nice little table in your notes to compare diamond and graphite and get learning it. And it will really impact you because these questions always come up in the exam. So here we're given a picture of another allotrope of carbon called Buckminster fullerene. Here we're asked to identify the formula of Buckminster fullerene. Now here you see it's just an identify question. This is really just testing your recall. This is just a fact that they have expected you to memorise. So the answer to this is C60. So if you don't know that already, add it to a flashcard and get memorising it. Here we're told that the air in the atmosphere is an example of a mixture of substances including oxygen, nitrogen, carbon dioxide and a trace amount of argon. Here we're given 3 different boxes, A, B and C, and we're asked to identify the mixture from the following samples. So the first thing here that would be helpful to know to be able to answer this question is simply what is a mixture defined as? So it's important that we know that a mixture contains 2 or more substances that are not chemically combined together. So that's going to be 2 or more different substances that are together but not actually chemically combined. So if we have a look here using that definition that we've just stated and look at these boxes, we should be able to see when things are chemically combined and when they're not. So in B, for instance, we have these darker circles and the lighter circles. Now, because they are drawn next to each other, actually joined together, that represents them being chemically bonded. So that could represent something like H2O or something like that. Whereas in C, you can see that we have got little pairs of particles, again stuck together, so chemically joined together. And there's nothing else, crucially, in B or C other than that identical substance. Whereas if we look at A, you can see we've got 2 different things. We have the dark circles that are existing all on their own. And then we also, as well as that, have these little white pairs. Now those white pairs are in a mixture with the dark circles. And we can see that because they're not chemically combined. So if you compare it to B, where all of those dots were joined up together, they're not here. You've got some black circles all on their own, and then you have the white circles separate to the black circles. So A is therefore a mixture. So we can fill in here, the mixture is shown by diagram A. So the different substances in the air can be separated. Here we're asked to identify the process that can be used to separate the substances in the air from each other. Tick one box only. So here we're asked to find the process to separate the substances in the air from each other. And like we've said, the air is a mixture. So we're not looking at separating any chemical bonds, we just want the different sections of the air. So let's remember we've got that oxygen, that nitrogen, the carbon dioxide and the argon. We need to separate them from each other. So the process that we will use to do that is fractional distillation. And that relies on all of those different components, say the oxygen and the nitrogen, etc., all having different boiling points. So that means we can heat it up, and at different temperatures, different components will end up changing state. And funnily enough, here we're asked to state the property of the substances in the air, which enables them to be separated using this method. And I've already kind of given you a hint here, haven't I? I've already said it. The property that enables us to separate them is the fact that the different components have different boiling points. And that's true of any time when you would use fractional distillation. It's when you have several substances in the mixture, all of which have different boiling points. So here we're asked to complete the sentence about isotopes. And we've got some words in the box that we're to pick from. Isotopes are atoms of the same element with a different number of something and the same number of something else. So this definition is such an important one at GCSE. We're going to use it all the time. So make sure that you learn this definition. So here, isotopes are atoms of the same element with a different number of neutrons, but the same number of protons. Like I say, that is a key definition and one that I'd really recommend that you add to your notes and your flashcards. It's really important that we know that fact about isotopes. So next up, we're asked to use the mass spectrum provided to calculate the relative atomic mass of the element. So the way that we're going to do that is by taking the mass of each isotope, multiplying it through by its percentage abundance, then adding all of those together and dividing through by 100. Okay, so what we're going to do here is we're going to do 2 times 36 plus 3 times 38 plus 95 times by 40. We're going to add all those together and then divide through by 100. So if I put those into the calculator, then I end up getting a relative atomic mass equal to 39.86. So there we go. So that is our relative atomic mass of this element. So now in part D, we're told that in the periodic table, argon is represented in this way here. And we're asked to write down the number of protons, neutrons and electrons in an atom of argon-40. So let's have a look at that representation. We should know that the bottom number is the proton number, or you may hear it called atomic number. Whereas this number on the top is the mass number, or you might hear it called the atomic mass. So the mass number is actually equal to the number of protons plus the number of neutrons. Whereas the proton number kind of does what it says on the tin, and it is equal to the number of protons. So if we go here and have a look at what we need to complete, the number of protons will simply be equal to 18. Whereas the number of neutrons, to work this out, we would use the number 40, which is equal to the number of protons plus the number of neutrons, and subtract from that 40 the number of protons, because the number that you're left with there is simply the number of neutrons. So we have 22 neutrons. Finally, we need to know the number of electrons. And the fact that we need to use here is that in an atom, which is a neutrally charged particle, the number of electrons is actually equal to the number of protons. That's a really important fact that we're going to use again and again. So using that fact, because we have an atom of argon here, not an ion, we're going to have the same number of electrons, so 18 electrons, as the number of protons. Here we're told that sulfuric acid is an example of a strong acid. Here we're asked to identify the ion present in sulfuric acid that makes it an acid. And here you see it's just an identify question. So this isn't like a big explain or anything, we just need to know this fact and have it memorised. So it doesn't matter that we're talking about sulfuric acid here, any acid under the sun, the ion present that is going to ensure that it is an acid and acts as an acid is going to be the H+ ion. So for B, when an alkali is added to the acid, a neutralisation reaction takes place. Here we're asked to identify the pH of the solution formed in a neutralisation reaction. So here it's very important, again this is just another fact that we need to know, that when neutralisation takes place, or if we just have any neutral solution, that solution will have a pH equal to 7. Here we're told that universal indicator is used to measure the approximate pH of a solution. Here we're asked to give the colour of the universal indicator when the solution is neutralised. So this here sort of follows on from what we just said. We would have had to have correctly identified that neutral solutions have a pH of 7. And here we need to know that when we have a pH of 7, universal indicator will turn green. Here we're told that we have 4 test tubes, each with a different metal, and we've added 20 centimetre cubed of dilute sulfuric acid to them. We made some observations, and here is a little table summarising them. So we can see that with sodium we had a violent reaction. With gold we had no reaction. With zinc we had bubbles of gas formed and the metal dissolved. And in calcium you can see that the bubbles of gas rapidly were released and heat was given off. So here we're asked to write the names of the 4 metals in order of their reactivity using that information that we just saw. So here we need to look at these and think, well, which of these observations would correspond to the most reactive of them? And I think looking at these, it's clear that the most reactive is going to be the one that had that violent reaction. So that here is going to be sodium. Cross that one out. So on the flip side, let's think, well, which is the least reactive then? And out of these, the least reactive is going to be the one that didn't actually have any reaction at all, and that is gold. So now we're left with just zinc and calcium, and we need to compare them and determine which of those would be the most reactive. So with zinc, we're told that bubbles of gas were formed, and calcium, we were also told that bubbles of gas were formed. But for calcium, the bubbles of gas were rapidly released. And that increase in the speed tells us that the calcium is what is more reactive. So I'm going to write down calcium as my second most reactive out of these metals. And my third most reactive would be the zinc. So now we're asked to complete the word equation for the reaction between zinc and sulfuric acid. So here it's important that we remember our facts. So whenever we have a metal and it reacts with an acid, we need to know that we will always form a metal salt and hydrogen. So using that fact here, if we go back and look at this equation, we're going to form zinc sulfate and hydrogen. And the reason why it's zinc sulfate is because sulfuric acid always forms sulfate salts. So that is our answer, and if you weren't aware of it, make sure that you know that this is the standard reaction of a metal with an acid. So now we're asked to calculate the percentage by mass of hydrogen in sulfuric acid. So to work this out, we need two things. We need to know what is the relative formula mass of sulfuric acid and what is the relative mass of the hydrogens within sulfuric acid. So let's work out the MR of sulfuric acid first. And in here you can see that we have 2 hydrogens, each of which have a mass equal to 1. We have 1 sulfur, which has a mass of 32. And we have 4 oxygens, each of which have a mass of 16. So calculating this, I find that we have a relative formula mass equal to 98. So if we look at within that formula, you can see that of the hydrogens, which is what we're interested in, we have 2 of them. So the mass of hydrogen within that is just going to be the 2 times 1, which is 2. So to work out the percentage by mass of hydrogen in sulfuric acid, we're going to have the mass of the hydrogen divided by the MR of that whole sulfuric acid, and then to change it to a percentage, we times by 100. So in this case, we will do 2 divided by 98 times by 100, and I make that to be 2.04%. And that there is our answer. That is the percentage by mass of hydrogen in sulfuric acid.
Well done for making it to the end of this paper. I'm really, really proud of all of your hard work. Go and have a break now, and then we can continue getting ready for physics paper 1. Ouch! This is why in some videos I explain scratches.